for having me. So this is actually work that started, sorry, Raghu is here. Raghu is here? Oh, there he is. So this work actually started, and we started talking about some of this stuff in 2012 when Raghu and I were at the ISMP meeting. And for a few years, as is always the case, I tend to be quite slow. We kind of, ambled along, and then when Jose had visited, we started doing some more of it, and my doctoral student, Afrouz, pushed this along. And one of the questions that came about was asked by Peter Glynn when I visited at some point. So this work pertains to variable sample size stochastic approximation. And some of you have seen some parts of this talk, so I apologize for the repetition. Let's just start with a very basic problem. We're interested in convex optimization problems. So if you have a problem where you're minimizing some function where the function f is convex and a approach is a gradient-based method where given some x naught, you essentially compute the gradient, use a step length, and move along the negative direction, right? It's well known that if f is strongly convex with a Lipschitzian parameter given by L, you can actually show linear convergence of the iterates. If you have weaker conditions, you can also derive rate statements, right? Our focus is on settings where you essentially have constraints. So instead of Rn, you have capital X, and this capital X is not necessarily a trivial set of constraints. So it's often a box. So things like box constraints are fairly straightforward. We're not interested in those. We're interested in nastier problems where you have nonlinearity. And when you do have this constraint X, which we were going to assume for the purposes of this talk to be closed and convex, you can use a simple projection. Now, I say simple. The operation sounds simple, but it essentially requires the solution of some optimization problem. It's a strongly convex optimization problem, but still, it could be quite painful. Okay? So that's the standard projected gradient method. And the stochastic approximation scheme that we're interested in is a variant of this where I don't use the true gradient, but I use a sampled gradient. Okay? So under suitable conditions on f and on the choices of the step length, you can show that xk converges to x star. This is well known for gradient methods. So if f is strongly convex, in the deterministic regime, you can show linear rates of convergence where q is less than 1. And if f is merely convex but differentiable, you can show that f of x bar k minus f of x star is of the order of 1 upon k. Okay? I want you to keep an eye on these rates because one of the foci of this talk is to try and bring together stochastic rates of convergence with deterministic rates, akin to what Raghu has done in the past, but with a caveat that we're looking at introducing a simulation budget or a sampling budget. So our interest, as I mentioned, lies in convex stochastic optimization problems. So instead, where f is defined as the expectation of some function, right? So f is basically mapped on x times Rd, where psi is a random variable that maps from omega, the sample space, to Rd. There are a host of applications. But the key point worth noting is that direct applications of the gradient method are impossible because I don't have access to the integral or its derivatives. Okay? And so the resolution that was first proposed by Robinson Monroe in the 50s was to use a sampled gradient, right? So you essentially take a sampled gradient and you use that instead. And under suitable choices on the step length sequence, you can guarantee convergence, right? So that's our setting, and that's where we're going to be using as a basis to start thinking about our scheme. So if you look at a vanilla stochastic approximation scheme, if Wk is the difference between the sampled gradient and the true gradient, you can look at the update, the stochastic approximation update, or the stochastic gradient update, as just xk plus 1 is defined as the projection of xk minus the sample. You move along the sampled gradient by a negative of the sample gradient by a distance gamma k, the step length gamma k, and essentially then you just project. Exactly what you did in gradient methods, with the one difference that you're using sample gradients. Okay? So this was back in 2012 when we started seeing Oren Osadal actually look at using subsampling ideas, and then Raghu did some wonderful work where he actually looked at trying to examine the rates of convergence. I'll talk a bit about those results. And we were inspired by the same idea with one simple difference, that we're interested in taking a sample size of nk at step k, and we terminate the scheme when the amount of samples that we consume exceeds m. So I've given you m samples, and I'm going to terminate the scheme when you consume those m samples. Okay? And you can see that nk is 1 for all k. This is just standard stochastic approximation with batch size 1. When nk is n for all k, it's just some stochastic approximation with a batch size of n, often called mini batch schemes. And if nk goes to infinity, you're essentially recovering gradient descent. Okay? So there are a host of shortcomings and challenges of stochastic approximation schemes. I mean, for those of you who implement these schemes, you know, some of these are pretty obvious to you. So there's a sensitivity to choice of step length sequences. And so a partial resolution of that has been achieved through long steps, right? Averaging and long steps. And this is work by Polyak and Juditsky in 91. And there's been other papers that have also used this framework. In 2009, there was some remarkable work by Nemirovsky, Juditsky, Lan, and Shapiro, where what they said was if you specify the simulation length, if I know something about the problem, then I can tell you the optimal constant step length that will guarantee me the optimal rate of convergence. Okay? And that optimal step length was d upon c square root k, where k is the length of the simulation run. And if I use this step length, I'm able to achieve the optimal rate. In related work, we looked at strongly convex problems, and we were able to show that if gamma k is chosen in an appropriate fashion, you can also recover optimal rates of convergence. And this was to answer the question, how do you choose gamma k, right? So generally, people used to just take gamma k as being a non-summable but square summable sequence, but there's a large number of sequences, and the choice of those sequences, you know, if you take a if you just use 1 upon k, that could be a remarkably poor choice. So one resolution of that was to say, well, let's use problem parameters in a sensible way to come up with this recursion. And this recursion is motivated by minimizing a suitably defined error bound. Okay? So this was work done by my doctoral student together with my colleague Angelia Nedic. This is Farzad Yousefian's work, where we were able to actually use this recursion, and this tends to kind of adapt to problem parameters. So you don't have to actually choose 1 upon k, you just utilize this recursion. Now, if you look at the convergence rate in projection steps, right? So deterministic gradient descent, if you have a strongly convex problem in this metric, you have linear rates of convergence, while stochastic approximation goes from here all the way to 1 upon square root k in terms of xk minus x star. If you have convex differentiable problems, the deterministic rate is 1 upon k, while the stochastic approximation scheme gives you 1 upon square root k, and that's the gap. So this is linear to 1 upon square root. This is 1 upon k to 1 upon square root k. There are several challenges. One big concern with stochastic approximation is if I give you 1,000,000 samples, you end up taking 1,000,000 projection steps if you use naive stochastic approximation. Look at this scheme. See, this scheme, if I give you 1,000,000 samples, that means you can take 1,000,000 sampled gradients, which means that you essentially run the scheme on top till k is equal to 1,000,000. Which means you project 1,000,000 times, which means you solve 1,000,000 optimization problems, okay? And that, in a lot of cases, is a fairly large burden, okay? It renders the scheme somewhat useless. So when x is not simple, there's significant computational complexity from a single projection, and if m is large, from the number of projections. And so there have been ideas that have been examined or suggested. So the first idea that we at least read of was work by Batsikas and Tsitsiklis, where they talk about batching strategies where they explicitly mention increasing sample size. So that was just kind of kept as an idea, but it wasn't kind of. There's a lot of work on inexact gradient methods, beginning with the ideas of Michael Friedlander and Mark Schmidt, where they looked at driving in the inexactness to 0 at sufficiently fast to get deterministic rates. Okay? In this regime, there was no bound introduced on the amount of simulation budget. There's also some work by Raghu Pashupati, with Peter Glynn, Soumyadeep Ghosh, and Fatma Hashimi, where they look at rates at which NK should also be increased to obtain consistency and efficiency. Okay, and they have a two-stage sampling procedure. There's also some work by Jorge Nosadal, which is what inspired us, where they also look at rate, they look at certain similar questions in the context of Newton-based methods. Okay? There's also work by Saeed Gadimi, where they actually came up with a bound like ours, but they don't actually proceed further. Just provide you with a bound, and they leave it there. Now, in the context of machine learning, where the function is where you consider only these types of problems, there are schemes where you can actually get deterministic rates of convergence and there's work by Shao and Zhang and a whole host of papers that have followed this. So this is called the SVRG method, the stochastic variance reduced gradient method. And the one point worth noting, and I'll revisit this question later, is that this class of algorithms, or this technique, requires that you compute the full gradient at some point, and intermittently. And that's not true in truly stochastic optimization. You can't compute the full gradient. So what is our motivation? We're interested in coming up with explicit rules for choosing NK such that we can get the the optimal rate or the near optimal rate in terms of projection steps and obtain the near optimal rate in terms of sampling or simulation budget. So what is the optimal rate in terms of simulation budget? Just based on information theoretic bounds, you know that given m samples, the best I can do is 1 upon square root m, okay? In terms of projection steps, I've already told you what those are. If it's a deterministic, strongly convex problem, the best rates are linear. If it's convex, it's 1 upon k. And if you're using an accelerated scheme, it's 1 upon k squared, right? But we know all of these tend to be, these are never achieved in the stochastic regime. The question is, can they be in a regime where the simulation budget is finite, okay? So what I should note is that we've been able to come up with results in the strongly convex and convex regimes where we increase the sample size at, either at geometric rates or at linear rates, or in some cases polynomial rates, but we consider both gradient schemes and what are truly Nesterov accelerated schemes. So up till now, when they talk about acceleration and stochastic approximation, they just use an extrapolation step, but the rate doesn't change. Our question was, can we actually take Nesterov acceleration and just change the sample size very naively and recover the 1 upon k squared result? And if we do recover the 1 upon k squared result, with what cost in terms of statistical accuracy is that rate achieved? If you look at the analysis of these schemes is not particularly difficult. And if you look at the paper, you'll see that most of the stuff is it's a bit laborious, but it's not particularly innovative. I mean, I think the surprise in this is how well it does. I don't think the theory is particularly, it is what it is. If you look at this, the main thing that you want to note is that when you write out the recursion, essentially what happens is the variance gets scaled by nk, the sample size, okay? So normally nk is 1, so this thing persists. So once you have this and then you write it out and you essentially go through a telescoping argument, what you're able to see is that when nk is raised at a geometric rate, you find that you can recover linear rates of convergence in expectation, right? And this linear rate is achieved at the point when you actually terminate the scheme. So when so it's not forever. It's not a non-asymptotic rate because you only have a finite simulation budget. Compare this with the standard result where you just get 1 upon k. Okay, so you get this linear rate of convergence, but that's not enough, right? What we want to know, what we would like to know is what is the impact on statistical accuracy? Can we actually recover 1 upon square root m? And it turns out that we have to be a little careful. So when I say square root m, this is going to be squared is less than, is of the order 1 upon m, so xk plus 1 minus x star is 1 upon square root m. So what you notice is that if the parameter which is used to update the sample size, right? So this has to be chosen in a sensible fashion. If it's chosen to be too small, you get a poorer rate. You don't achieve the optimal rate. If you make sure that it's sufficiently large, but it obviously has to be less than 1, what you find is you achieve the optimal rate, okay? Now remember, standard stochastic approximation also achieves the optimal rate in terms of simulation budget, but it does so with a significant computational expense. So let's remind ourselves of what the expense is. If I use standard stochastic approximation, I take 1 sample at each point. Let's assume that I use a diminishing step length. I end up with m projection problems or m optimization problems, and I get a rate of 1 upon k in projection steps and 1 upon m in terms of statistical accuracy. And remember, in the first row, m is equal to k. Let's take our scheme, where rho is greater than q. What you find is from m, you've gone down to log m, which is a big reduction. And what you've got in terms of rate is, of course, the linear rate. It's not surprising, right? You're increasing the sample size at a geometric rate, so you expect to only have log m many steps. And you are able to achieve the optimal statistical accuracy. So there's no loss. Now, if you use a naive batching rule, you might think, why don't I just batch? But if you batch and use a batch size of n, the statistical accuracy worsens by a factor of n, while the computational cost goes down by a factor of n. Right? Because if you have a batch size of n, you only end up taking approximately m upon n steps. Okay? So this is a big difference, right? Because traditionally, or not traditionally, in general, if I give you 1 million samples, that means 1 million optimization problems for standard stochastic approximation. Here it's log of 1 million. So you can imagine that it's a significant drop. Now you might say, well, there's a big O constant in each of these. How does this compare? It turns out that actually the empirical behavior is very good. And we actually quantify this more precisely in the convex regime. Okay, any questions? Okay. So now let's take the convex case. So in the convex case, the only requirement that I have is that I need a bound on the initial iterate from the solution. And this is not really a fair assumption. It's just a requirement that I need to choose C1 such that this holds. So it's just a choice, right? If this doesn't hold for this just make it larger, right? So don't get caught up in all the math. The main point worth noting is I'm increasing the sample size at a rate n0 k raised to a. So when a gets close to 1, it's nearly linear. Okay? And so what happens is that when a gets close to 1, this is of the order of 1 upon k, which is the deterministic rate. And you can see as a gets close to 1, you're able to come down to this rate here becomes 1 upon square root n. So you're able to achieve the optimal rate. You're able to achieve the optimal statistical accuracy while achieving the optimal rate in terms of projection steps. Now you might say, and this is worth noting. Compared to standard stochastic approximation schemes, this k is much smaller, right? Because you're actually raising the sample size. So just because you have a better rate doesn't buy you anything. The only reason it buys you something is because you end up taking less steps. So let me I'll emphasize that later. So if you look at Nemirovsky's result, this is the result they have. This is the optimal constant step length. You get this statistical accuracy, which is optimal. And since k is equal to m, that's the rate in terms of projection steps. If you use batching, you get a similar result here, but you have this worsening here. Okay? So if you batch, there's a worsening of the bound by approximately square root n, but you have a savings in terms of projection steps. So I want to just use that to kind of compare our method. So if you look at the first row, so the first row is standard stochastic approximation, optimal rate in m, and the rate is 1 upon square root m in that. And how many steps do you need? Approximately m. Okay, if you look at our scheme, variable sample size stochastic approximation, you end up with a similar rate with a slightly better constant. I'm not a big fan of using these constants to ascertain how our scheme is doing. At least you know that it's of the same order of magnitude, right? But I wouldn't get too carried away with looking at this constant and say, oh, it's better, so the scheme does better in practice. I'm not one to buy that. What is worth noting is that the rate in terms of projection steps is 1 upon k, approximately. But you can't compare this apples to apples to that one. The reason is, the other one, you end up taking more steps, right? And this one, you take less steps. So what you want to look at is, when you terminate, is the accuracy similar? And that you can see is similar. But what is important is you've only taken square root m steps, right? So if you had 1 million samples, you ended up just taking 1,000 solving 1,000 projection problems to get a solution of similar accuracy. And that's worth emphasizing. Okay? And you can show that's the case both for diminishing and for constant step length. But it turns out if it's diminishing, you only achieve that when if you set it as gamma k is k raised to minus b, you only achieve the optimal rate if b gets closer and closer to 0. So effectively, it says that you can only achieve these rates when you have a constant step length. So that made us think, should we try and think about acceleration? So those of you familiar with these schemes, you'll see this is very similar to Nestrov's original statement of the algorithm. For those of you not familiar, there's a seminal paper by Uday Nestrov in the mid-'80s, where he showed that the optimal rate of convergence for gradient methods by using this kind of extrapolation scheme is 1 upon k squared in function values, as opposed to 1 upon k. Now, that rate has never been achieved the best of our knowledge, in the stochastic regime because you don't increase sample size. You generally keep them constant, or you have a batch size. What we did was a very naive restatement of the scheme by just using a sample size of nk. And we terminate when summation of nk exceeds m. That's the only change. And our question was, can we achieve the rate? And if we achieve the rate in terms of projection steps, what do we lose? Okay? And it turns out, in the strongly convex case, you get the linear rate, which is what you expect. And what is notable is that you get the optimal statistical accuracy of approximately 1 upon square root m. So this is 1 upon m plus 1 upon square root m. If you look at the case where it's just convex, what happens is that it's a little nastier. What you find is that so I want to just remind you of one thing. Here, we increase sample size at a geometric rate, which is pretty fast. But when you reach here, you're increasing it at k raised to a, and a is something you have to choose. So an arbitrary choice of a will not work. It turns out that a has to be larger than 6, which means you're increasing this at a crazy rate to recover the rate of convergence. Right? So if a is greater than 6, it turns out that you get 1 upon k squared. Right? Because if a is greater than 6, you find that all of this stuff is this goes away. This is a positive constant. You get 1 upon k squared. So you're able to achieve the optimal rate, but it's at a ridiculously fast update in terms of sample size. So that made us worry about this scheme because it looked like a theoretically interesting scheme, but practically useless scheme, right? But more on the numerics later. When we actually analyzed what the statistical accuracy was, and we expected it to be worse, but we were able to get something, but it wasn't the greatest result. The result was that instead of being 1 upon square root m, or 1 upon m raised to a half, it was 1 upon m raised to 2/7. So we lost a bit. Okay, and we were worried how significant that disparity would be when we actually ran through the numerics. Okay, so just to remind you, what we've done up till now is, in the case of strongly convex problems, by increasing the sample size at a geometric rate, we can get the optimal rate of convergence and the optimal statistical accuracy. In terms of convex differentiable problems, by increasing the sample size at approximately at the rate of k, you can achieve the optimal rate of 1 upon k and the optimal statistical accuracy. In the accelerated regime, you have to increase it at least at k raised to 6. And it turns out we could weaken this a bit, and I'll show you what we do next. You can actually achieve the optimal rate of 1 upon k squared, but you lose something. Instead of being 1 upon m raised to a half, it comes down to 1 upon m raised to 2/7 plus epsilon. Okay? So a quick recap of that. So AC VSSA just means accelerated VSSA. Okay, so I increase it at k raised to minus rho, and there should be a floor here. So remember that the amount of steps, again, is of this order. There's a typo here. It shouldn't be 1 upon 1 plus m. There's a mistake. It should be log rho 1 plus m. Okay, I'm sorry about that. And this, if you're raising it at a factor of k raised to 6, where a is 6, you end up taking m raised to 1/7 steps. It's a fairly small number of steps. So you have to really wonder if this is going to be useful. So again, optimal rates in k, but suboptimal rates in m. Okay? So a natural question that, so this is just follow-up work that I'm going to present here. And this is motivated by problems in machine learning, where you have structured non-smooth optimization problems of the form f of x, capital F of x is given by fx plus gx, where f could be an expectation, right? And g may be non-smooth. Okay? And this is a fairly broad class of problems. And why did we consider this problem? Well, in part because there's some seminal work by Mirbek and Mark Taboul where they extended Nemirovsky's work to incorporate this class of problems. Okay? And for this class of problems, they're able to get optimal rates of convergence despite the non-smoothness. Right? So you remember that Nemirovsky's original method required smoothness. Now what we find is that you can have some non-smoothness, and this G can't be arbitrarily non-smooth, in the sense that you need to be able to compute a prox operation efficiently. If you can do that, then you can actually get a rate in terms of prox operations. Right? So a special case of this is machine learning, where f is given by a summation of fi of x divided by n. And there's been work in this, and this is just an extremely paltry review of this literature. There are like millions of papers. In fact, while I'm talking, there were probably 4 published. Right? So So there's work by Roux et al. Where they looked at stochastic average gradient, where you actually store a gradient and update that stored gradient. And the de facto standard, based on what I've heard from some of my machine learning colleagues, is SVRG, which is stochastic variance reduced gradient, where what they do is they intermittently compute the full gradient, and then they compute a bunch of sample gradients. Okay? So machine learning in that sense is interesting, because their problems are assumed to be deterministic enough or small enough that they can compute the full gradient, yet not so small that they can consistently compute the full gradient. Okay? This is distinct from, say, stochastic optimization, where we can never take advantage of the full gradient. If you look at our framework, we have a very naive scheme. We just increase sample size. Right? I mean, it's almost a daft scheme, and you wonder why it actually works. But it's actually a very naive scheme. All it does is just increase the sample size. But we don't need the sample space be finite, right? And we never need the full gradient, unlike SVRG or Prox SVRG or their variants. Okay? So in this case, the accelerated proximal method, what we do is we compute the prox. So this is where all the complexity of the non-smooth function is captured. So if you can't compute that prox operation efficiently, then this scheme is not going to work, right? So one of the caveats is that you need to be able to compute this prox operation efficiently. If you can't do it, right? And then there are these two simple updates. And we've been able to kind of extend some of these to get them to work for stochastic optimism. This is a little more that I'm not putting up here because it's a little technical. And the scheme is the same. When I consume the simulation budget, I stop. And otherwise, I just keep iterating. One thing you're going to observe in the numerics is that, this is actually it's a typo. It should be rho raised to minus k. I'm sorry. So that choice of rho is essentially something that you can't be arbitrary. It can't be arbitrarily selected. It has to be chosen in accordance with problem parameters such as the convexity constant and the Lipschitz constant. Right? So there are lots of limitations of these schemes, and one clear limitation is its reliance on problem parameters. Right? So I'm pretty open about the fact that gradient methods, at least if you're trying to provide rate statements, are characterized by this deficiency that we need some information, and sometimes this information is hard to estimate. Right? And the other big kind of shortcoming of this scheme is that we assume that sampling is cheap, that we can sample nk, where nk could be arbitrarily large. And lots of instances where the sample requires you to go and run some experiment, I mean, this scheme wouldn't work. Okay? Now, the effort in terms of that sampling is not captured. That's something we're considering. How do you actually capture the cost of sampling in this frame? You can't get a rate which is arbitrarily good in terms of the linear rate, because that rho that you choose has to be chosen based on some bound. Right? It has to be sufficiently large. Okay, and if it isn't sufficiently large, then you lose the statistical accuracy. I need some Lipschitzian properties like before, but I only need the Lipschitzian properties on the smooth part. Okay, I need some requirement on the initial iterate, right, in terms of its distance from f star. And if that is the case, then I can get again a linear rate of convergence. Okay, a linear rate of convergence. The rate is a little different because I have a theta and a rho, and this theta depends on alpha bar. Okay, I haven't put alpha bar here, but alpha bar is something that is proportional to mu upon L. And so once you have that, you can get the optimal rate in projection steps. But if you get the optimal rate, the question is, what is the loss in terms of statistical accuracy? Not much. You get the statistical accuracy that you desire. So these results are just analogs of the results for the smooth regime. If you look at merely convex regimes, and again you raise nk at a suitable rate, here we did a little more analysis, and what we found was that you can actually qualify this a little more. So if A is greater than 4, this is the rate you get. Okay? And if A is between 2 and 4, then you get a rate which is slightly worse. Because look, if A is between 2 and 4, instead of being 1 upon k squared, you get a rate which is 1 upon k raised to A plus 1 or something, which is where A is between 2 and 1. So you don't get 1 upon k squared. You get a slightly slower rate. So if A gets closer and closer to 6, you achieve the optimal rate in terms of projection steps, but you lose something in terms of statistical accuracy. So we started running these, and I'm going to spend a little more time on numerics because I want to kind of talk about what the shortcomings of the schemes are. Right? I don't want to just kind of push this. I think this thing has benefits in certain regimes, but in certain regimes it may not. Right? Okay, so this is a smooth optimization problem. I've got some polyhedral constraint, and I'm minimizing a utility function. Okay, so this is a problem that shows up quite often in a networked regime. Okay, and what I do is I provide a budget of 10,000, and I allow for 30 replications. Okay, because when I'm basically computing for the convex regime, what I need to provide you with is basically an average over all these. So, right, the empirical average. Okay, so let's look at the first problem, the strongly convex regime. So let's talk about this table. So in this column, I've essentially got standard stochastic approximation. So what this does is essentially it just takes 10,000 steps. This is the theoretical bound, and this is the empirical error. And that's what you'd like to calibrate against. Okay. So if we run variable sample size in a strongly convex regime, we require, if rho is aggressively chosen as 0.9, which means that the sample size is growing much faster, what you find is that you're able to achieve an optimal an error of 6.97 e raised to minus 4, but you only need 66 projection steps. So when I say steps, you want to think about 66 optimization problems. So it's a big difference because essentially each optimization problem, if it took you a few seconds, then you're cutting at least 2 orders of magnitude on the time. Okay? Now, if you raised rho to 0.99, you can actually get better error, but then you're doing it at some computational cost. So you end up spending a little more time computing. So this is for strongly convex problems. So here you're raising sample size much faster. Now, if you use convex problems and you have diminishing and constant step, let's just look at this one. Okay. So if I use standard stochastic approximation, I get 7.5 e raised to minus 4, and that's the theoretical error, 2.318. And how do I get that? That's basically Nemirovsky's bound, which is based on the optimal constant step length. If I use variable sample size where I increase it at k raised to a, and remember the optimal rates come when a gets closer and closer to 1. So you can see that the number of steps is 180. It probably goes down to 150 if a goes to 0.95. The error is, in this particular setting, is superior. But I don't want to get caught up in being better or worse. I just want to make sure it's the same order of magnitude, right? Because these are essentially synthetic instances. I don't want to sit around believing that this is what's going to happen in practice. I just want to make sure that for most of, whether for all the problems that we are checking, things are in the same order of magnitude. And what you find is that the bounds that you get are actually well within and that's exactly what we expected. Because remember, we showed this. I showed you that I have a slight improvement in the constant, right? So there's a slight improvement in the constant based on the choices, okay? And so you see that when you actually run these, right? There's a slight improvement in the constant. Now in diminishing step length, you see that the best results come when B gets closer and closer to 0, A gets closer and closer to 1. Okay, so which suggests that, don't use a diminishing step length. Basically use a constant step length with k raised to a, right? So in some sense, we're able to recover the need to use constant step lengths. The accelerated schemes proved quite surprising, okay? So in the case of acceleration, remember, I'm increasing the sample size at a much faster rate. Well, in the linear, in the strongly convex cases, again, it's at a geometric rate. And here you can find that, when rho is 0.7, so it's very aggressive, you need only 24 iterations, right? So basically, by solving 24 optimization problems, you've actually got an error which is, approximately 1/3, or at least the same order of magnitude as what you would get with stochastic approximation, right? So there's a reasonable jump there. But what I want you to look at is this. So remember, I showed you. I said, look, the statistical accuracy, there is some loss, and you see it here. Okay, so look in the convex regime. So remember in the convex regime, I told you, instead of 1 upon square root m, it's 1 upon m raised to 2/7. So we expected that the algorithm to perform very poorly. Because it's m raised to 2/7, we just assumed. Now, and you can see the bound is much worse. It improves as a gets closer and closer to 6, right? That's where it actually is literally minimized. But still, it's worse than what you would get with standard stochastic, right? But in terms of behavior, it's significantly better. In fact, there are choices of A for which it's even better. And the number of steps in this particular case was surprising. We only needed 6 steps to get a solution. So we ended up solving this problem in 1,000th of the time. If you don't take in the time to sample. If you take in the time to sample, it's still not too much because this is a synthetic problem. On log scale, you can see this, right? So this is the accelerated scheme, and this is VSSA with different choices in terms of the rate at which you raise the sample size. If you raise it slower, you end up taking more iterations. You raise it, if you raise it faster, you end up taking less iterations. The accelerator is always, because you're increasing at a much faster rate, it tends to be faster. In the convex regime, you can see that the disparities are even more pronounced. One of the questions that so this was non-smooth, right? So for the non-smooth setting, we wanted to have a look and see how this did compared to de facto standards for machine learning like SVRG, okay? So we looked at what is called the fused lasso problem. So this was a model proposed by Tipshirani and I think it was Tipshirani and Hasty, I'm not sure, but it was in the early 90s. And the idea is that instead of standard lasso, what you require is that the consecutive betas have to satisfy some sort of constraint. So projecting on this is a bit more painful. So again, I want to point this out, that if I didn't have any kind of set to project on, this entire discussion is, can be omitted because I don't really care. The projections is what I'm really worried about. If I don't need to project, don't waste your time with this. Just use standard stochastic approximation. If you have to project, you can recast that constraint as just using this indicator function. And for this class of problems, we can compute efficient prox mappings. So remember, in this particular case, n is 1,000. These are still small problems. And the reason why we kept n as small is because SVRG needs to compute the full gradient. Okay, and so we just wanted to check it for SVRG. Because we don't need, we can actually work with the expected value problem. But SVRG needs n to be finite. So we use m as 7,500. We ran 50 replications. This is some information about how we, how we generated the data. So this is a strongly convex problem. Okay, it's a strongly convex problem. So for different values of rho, so rho, remember what rho is. Rho represents the rate at which you raise the sample size. It's rho raised to minus k. Okay. You find that you need very few iterations, and you're able to achieve errors which look extremely good, right? It's 10 raised to minus 11. So if you're wondering why that is the case, the reason you're able to achieve that is because when you increase nk, at some point you hit the upper bound of 1,000. If you hit 1,000, then you're taking full gradients, right? So then it's obvious you're going to do well, right? So it's not a great comparison, but this is what we just started with because we just want to see if you compare apples to apples with SVRG and keep the amount of information the same, how do we compare with SVRG, right? So, but in this case, it's not surprising, right? I mean, using a full gradient method, you're going to get high accuracies. It's not particularly surprising. So what we did was we increased n, and now what I've got here in these 4 columns is variable sample size. This is called the accelerated proximal method, which is what we have. And what we've done is we've compared it to SVRG. Now, the way we've done this is we've said, OK, I'm going to run SVRG, and I've actually calculated how many gradients SVRG used versus us. And what are gradients? Gradients tell you how much information we've used. So we've used less information. I wanted to deliberately use a little less information. And when you use this information, the last 7 steps were exact gradients. Okay? Here the last 4 were exact. In this case, there were more exact gradients because the way SVRG runs is it does exact gradients, a bunch of little steps, exact gradient, bunch of little steps, and so on. Right? So they end up taking more exact gradients, but we seem to get better accuracy just because of the way the method, the algorithm is structured. Suppose I actually ran the scheme and I actually checked to see how many projections you take. Because here I've just told you information, right? I haven't told you how much time the method actually takes, right? So if you look at this, whenever we take a gradient step, we project, right? When they take a gradient step, when they take a full gradient step, they project, and when they take a sample gradient step, they project, right? So they end up taking, say, SVRG, when they have 100 inner iterations between every exact gradient, they end up taking 700 because they have 7 exact. So 7 exact and 100 between, which means 700 iterations, which means 700 projections. In this one, when they have 300, they end up with 2,100 projections. right? We only needed 19 iterations, which means we had 19 projections. So the point is that we get better accuracy, but we're able to do it with far less effort. So this is literally, so if you look at 500 iterations, which is this one, this is the one that we compare to. So I've shown you a graph, but you don't want to look at this graph and compare, because the way the x-axis is different. So the way my student has done it is a bit misleading. It suggests that you're on the same graph. But you can't compare them. The reason you can't compare them, I mean, the way you want to compare them is just to see in terms of projections. Right? But if you look at exact gradients, yeah, after 7 exact gradients are done, but between these, they've also projected. Right? So they've basically run 700 projections, 2100, 3500 projections. And these projections could be quite nasty, as I've emphasized throughout. You know, it's pretty clear that if you increase rho, you're slowing down the scheme. Well, if you increase rho, you're taking more iterations, right? Because when rho is larger, that means the sample size is growing at a slower rate. So initially, we thought that if it's growing at a slower rate, then you're using the diversity of the information in some effective fashion. It turns out that if a rho is smaller, you're taking less steps, and you're getting increasingly exact gradients much faster. And that seems to work well, right? Because look, here you've taken just 15 steps, and you're reaching an accuracy of 10 raised to minus 10. Now, you might say, can you keep going? Well, no, you can't, because there's a lower bound on rho. And that lower bound is really based on problem parameters. So I can't arbitrarily reduce rho. In this case, the problem was nicer. I could bring it down to 0.45. But in general, you know, that's one of the shortcomings. I need to figure out how to estimate those parameters in practice so that I can choose the rho sensibly. Right? That's not that easy to do. So what we've done is we've considered a suite of variable sample size approximation schemes. And essentially, we're able to get linear convergence here and get optimal rates, optimal statistical accuracy. In the case of convex differentiable problems, you're able to show that the empirical error decays at a near optimal rate when you increase sample sizes at a near linear rate, while the empirical error decays at the optimal rate. Okay? If you have convex differentiable and structured non-smooth, you can actually get the optimal rate in terms of projection steps, but you see a slight decay in terms of statistical accuracy, and I don't know if this is, you know, it's clear that you can go all the way to m raised to half, but it may be that we have to choose our sample size sequence in a different way, right? So this is like our first very naive attempt where we just threw the first thing that we thought of. And it may well be that there are better choices out there. Clearly, there's a gap, right? I mean, the best you can do is m raised to half. So the main thing I want to kind of remind you with, kind of leave you with, is the fact that we are able to kind of achieve these deterministic rates upon termination of the scheme. These are not non-asymptotic rates. And, you know, I don't want to kind of pose this as the panacea for all our ills and world hunger, right? It's able to deal with settings where sampling is cheap, where you have access to problem parameters. But the one thing that I think is worthwhile considering is that the success of nonlinear programming is predicated on the access to a fast subproblem solver. So if you have good QP solvers or good linear system solvers, you know, LU solvers for LU decomposition, those were crucial in terms of solving large-scale nonlinear programs. And so the hope is that this can be used as a solver for structured stochastic convex programs so that you can solve more general stochastic nonlinear programs. So if you look at some sort of approximation, QP approximation or a convex approximation, you couldn't consider this before because it would take you far too long to get a solution. But the hope is that this avenue will give us access to quick solutions via solving this subproblem. Okay, so I'll end here and take questions. So when I say exact gradient, in the case of machine learning, it just means computing the gradient with respect to all n functions. Yeah. Well, not this. Well, I guess when you talk about samples, you're talking about this problem as being a consequence of a sampled problem. But let's, you know, as an optimizer, I just look at this problem. I look at this problem as a problem that's been given to me. It's just some f of x. So the exact gradient just means using the gradient of f of x. So SVRG would use the gradient intermittently. Well, SVRG, you have to be careful. It does use samples along the way, but intermittently it uses the full gradient. So it'll use a full gradient, then it'll take sample gradients where it'll take one of these, and take a step. And it'll keep doing this. And this is called an inner iteration in the parlance of SVRG. When I say samples, I'm talking about sampling, probing the oracle, right? As a statistician, you look at this and you say, this is itself the samples that have been given to you. So I'm varying the sample size. So what we do is, suppose you assume that in this case, n is say 10 raised to 8. Okay? So, and suppose I give you a budget of say 10 raised to 10. Okay? Which means that I can only take 10 raised to 10 gradients of these little FIs. So I start by saying n0 is whatever, say it's 1. And I increase this. When the summation of nk exceeds 10 raised to 10, I stop. Uses the same information, but it requires 700 projections onto the set x. We require far fewer. And the reason why this is important is when x is a complicated set, that projection problem is costly. It does. In fact, that was our question to the folks in machine learning, right? So if it converges linearly, why are we worried about taking these little gradient steps? So our goal was just to compare with SVRG. We're not justifying that SVRG is the best algorithm out there. But the point is that we've done exactly that. But despite the fact that it's huge, they also have to take all these projection steps, right? So there's a gradient evaluation which is painful, but they also have the set they have to deal with, right? Just the way I've chosen it naively, right? I've just taken this polynomial thing which grows. Maybe there's another choice of sample size sequences that might allow me to achieve that rate, or maybe, it may well be that somebody can show that there is no better rate that you can achieve for this class of schemes. I don't know, both are. In the case of strongly convex, it was geometric. In the case of this, it was polynomial. So it's achievable for the strongly convex. For the convex, I don't know. I have no idea. The best we could do is 2 upon 7. We do know that there is a bound of m raised to half. That's the canonical, right? But you're right, I don't know. I have no idea if that can indeed be achieved. The question is that if you knew that, what more could you do? Right? So if you think about this method, what is it doing? Well, it's achieving the optimal rate in terms of the steps, which is actually kind of a bit spurious, right? Because the number of steps it takes is not, but it achieves the optimal accuracy and you're able to cut it down. So my question would be, what am I trying to get that I'm not getting yet? Because here I don't have that information. I'm able to increase it at this naive rate and recover the optimal statistical rate except for one of the settings. So you're saying, can we use some other information to guide the choice of the sample size sequence? I think Raghu probably, he's been working on stuff. I think they do a much better job in terms of selecting this. Ours is pretty naive. We just have this deterministic rate, and we wanted to see if you're able to actually capture something in terms of statistical accuracy. But I think they work a little harder in terms of figuring out the sample size. Am I correct, Raghu? So I think one thought there is that if you have a malicious gradient, and if you average across this, what's going to happen is that clearly these, let's assume that these gradients are from some other oracle, right? So it could be that now when you average this, you're not going to get the true gradient. You're going to get some gradient with some bias, right? So there are results where people are able to derive error bounds with some bias. And so what I expect is that you need some information about these malicious gradients so you can get some understanding of what this bias is. And then all you can show is that you converge to a point which is in some ball where the ball is of the size, the size of the ball is proportional to some bias, right? So you converge, you'll get the rate results, I think. What you'll miss is that you're not going to get asymptotic convergence. Oh, sorry, you won't be able to get rate statements to the solution. You're going to have this error. Well, what you'll get is something like this. So suppose you have this, you'll get 1 upon k squared plus something that just doesn't decay. It's something like B, which is the bias. So you'll get something showing up, right? And so that's something that people have already done, where they've said, suppose the oracle is corrupted by bias, can you get results? And there are results for that. But the question, I think, the question that you're asking, and John Ming and I asked, was that how do you if somebody didn't tell you, give you an ex ante bound on this, how would you? That's a good question. We'll have to.